Welcome everyone to week 10 of our problem solving sessions for the course Electronic Theory of Solids. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Solid State and Structural Chemistry Unit SSU of the Indian Institute of Science, IIC Bangalore, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL-PMRF TA for this course. Sorry about the little background noise that is coming from my laptop's fan. Just check if recording. Okay. So let us start with our today's session. So let's start with our problem number 1. So in problem number 1, what is given to us is, consider a system of 3 spins S1, S2 and S3, each of which can take values +1 and -1. The energy of the system is given by the energy that equation is already given to us, which is minus J S1 S2 plus S2 S3 plus S3 S1. Sorry, where J is a positive constant, and we have to find what is the minimum energy and the corresponding number of spin configurations. This we have to find. So here, so first, what is given to us? Again, we can see that basically we have 3 spins. Okay, S1, S2, S3, and all have the values plus -1, and the total energy is given by minus J S1 S2 plus S2 S3 plus S3 S1. Alright, this is the energy equation, and then so first of all we have to find this. We have to find the minimum energy. What is the minimum energy? And also we have to find the and corresponding to that minimum energy, what is the corresponding number of spin configurations. So first we will find all the possible spin configuration and their energies. We have the spin values could be +-1, and an energy equation also that is also given to us already. So this is a simple problem. So we will just take all the possible value of spins S1, S2, S3. Okay, and then correspondingly we will find our energy from this equation. We will find our energy. So let's say S1, S2, S3. One case could be all of them could be 1. Okay, and total, as we have seen in the previous session as well, total they are going to be, because there are going to be 2 values for S1, 2 values for S2, 2 values for S3. So total number of spin configurations that we can consider here. So that will be equals to 2 options for your S1, 2 options for your S2, 2 options for your S3, to total 8. So total there are going to be 8 spin configurations that we are going to have, and we already have the this equation for the energy as well. So we just have to take different values for the spins and correspondingly find the energies, and then we have to find the configuration for which we get the minimum energy in this problem. So first one would be each spins have the value +1. So if you put it there, then what we get the energy minus 3J. Alright, that is easy to find. Then the other configuration will be 1, 1 and -1, and if we put that there, then we get 2 minus 1, which will be 1. So what we get is sorry, we are going to get like for S1, S2 we get +1. From S2, S3 we are going to get a -1. From S3, S1 we are again going to get a -1. So it will be -2 + 1 will be -1. -1 times the minus J will be +J. So we get +J here. Similarly, if you take 1 minus 1, 1, then the S1, S2 will give you a -1. S2, S3 term will again give us a -1. S3, S1 will give a +1. So -2 + 1 will be -1. -1 times minus J will be J. And similarly, you can check the other combination could be this -1, 1, 1, that will also going to be J. Then if we have -1, -1, 1, so for S1, S2, -1, S3, 1, you can check that S1, S2 will give us +1, S2, S3 will give us -1, and S3, S1 will again give us -1. So we again get -2 + 1, that will be -1, and -1 times minus J will be J. Alright. Similarly, we will get -1, 1, -1 will also give us the energy J, and the other configuration, which is 1, -1, -1, that will also give you J. And the last possible configuration will be all 3 of them will be -1. So that will give you minus 3G. Okay, because you get S1 S2 minus 1 minus 1 minus 1 minus 3. Uh, so sorry, this will give us actually plus 3G. Sorry, what we have is okay. Sorry, yeah, this will give us minus 3G because S1 S2 will be minus 1 minus 1 will be plus 1. So we have plus 1 plus 1 plus 1 plus 3. 3 times minus J will be minus 3G. So here we can see that among all these energy values, these two are the minimum. They are actually same, which is minus 3J. So the minimum energy that we can get. So the problem was first is asking what would be the minimum energy. That is we have found it would be minus 3J. And then what is the corresponding spin configuration? So there are two spin configuration. One configuration when all of them are plus 1 and when all of them are minus 1. So basically we are considering of complete ferromagnetic configurations are giving us the minimum energy. Ferromagnetic spin configuration will give us the minimum energy. So the minimum energy that will be equals to minus 3J, and the number of spin configurations that will give us this spin configurations. So in total we have 8 possible spin configurations, and among them we have seen that 2 of them will give us this minimum minus 3J energy. One case will be when all the spins have the value plus 1 and when all the spins have the value minus 1. Alright, so this is our answer. Okay, so number of spin configurations. Alright, let's move on to problem number 2 then. Okay, so now in problem number 2, what is given to us? We are given the Hamiltonian for 3 Ising spins S0, S1, S2. Taking the values again plus minus 1 is minus J S0, S1 plus S2. Okay, so we are basically given the Ising spins are given to us earlier also. So for Ising spin we just have spin in only one of the directions, let's say SD direction, and we have these 3 Ising spins S0, S1 and S2, and each one of them can take the value plus minus 1, and the Hamiltonian is given to us, which is minus J times S0, S1 plus S2. Now if the system is in equilibrium at temperature T, what is the average energy of the system? Okay, so what it is asking, it is now asking us what is the average energy. So as you know, whenever we talk about the average energy, we have to as we have done in the previous session as well, we will first find the partition function, and then using the partition function we will find the average energy. Okay, so here for this problem we have the Hamiltonian minus J if we write what is given to us, we are given that we have 3 spins S0, S1, S2, and each of them can have the value plus minus 1. Okay, so total number of spin configuration. So this is going to be the same as you can as you might guess. Basically this is basically the same problem, or is that our Hamiltonian or the equation you can say for the energy, our energy function, that has changed. Okay, it is now minus J S0 times S1 plus S2, but the number of spin configuration they are going to be the same, so the energy values will change, and in this problem we have to find at an equilibrium temperature we have to find the average energy of the system. So again we have to do the same thing. Total number of spin configuration are each of the spins they can have either plus 1 or minus 1, so they have 2 possibilities. So in total we will have 8 number of spin configuration, and the Hamiltonian that is given to us, which is our energy, which will give us our energy values. So that is given to us, it will be S minus J times S0, S1 plus S2. Alright, so let's say we have S, so basically we have S0, we have S1, we have S2, and then we have the energy value that we will get from our function of Hamiltonian function. Alright, so now one case will be S0, S1, S2, all 3 of them are plus 1. Okay, if all 3 are plus 1, just put plus 1 value. S1 plus S2 will get 2, S0 1, so what we get is minus 2G. Another case will be 1 1 minus 1, Okay, S0 is 1, S1 is 1, S2 is minus 1. In that case, S1 plus S2 will be 0, so the energy will be 0. Similarly, if we have this case 1 minus 1 1, S1 plus S2 will be again 0, the energy will be 0. Then if we have a minus 1 1 1, then S1 plus S2 will give us 2. S0 minus, we take that minus with J, so that we get minus J times S0 will become 1 J, so J times 2 will be 2J, so we get an energy 2J. Then other could be, we could have minus 1 1. So if we have minus 1 1, so again S1 plus S2 will become 0, so we will again have a 0 value. Similarly, if we have minus 1 1 minus 1, that energy will also be 0. And if we have 1 minus 1, then minus 1 S1 S2 are minus 1 minus 1, so S1 plus S2 become minus 2, S0 is 1, so we get minus 2 times minus J, we get a 2, we will get 2J value. And then we have minus 1 minus 1 minus 1, so all three of them are minus 1, minus 2 times minus 1 will be 2, so what we get is energy is minus 2 times J. Right? So these are all the spin configurations and their corresponding energies. So this we have already found. Now we have to find the average energy. For that, first we have to find the partition function. So this is our partition function. So that we know is given by e to the power minus beta ei, where beta is 1 by kBt. I am not writing beta. Then correspondingly, you just have to put all of the energies. So all the all the non, so what energy, so e to the power minus, so we get, basically we have three energy values. Either the energy is 2J, either the energy is 0, or either energy is minus 2J. So for case energy is 0, these are you can say 4 cases. So 4 cases when the energy is 0, e to the power minus beta 0 plus 2 times, in 2 cases we have energy 2J, it will be beta 2J, and it is 0, and in 2 cases we have energy minus 2J. So what you are going to get, e to the power 0 is 1, so 4 plus it will be 2 times e to the power minus 2 beta j plus 2 times e to the power beta 2j, 2 beta j. Alright, and again we can just take this common. It will be e to the power 2 beta j plus e to the power minus 2 beta j. So again, as we know, so this we have seen a lot of time now. So cos hyperbolic is basically e to the power x plus e to the power minus x divided by 2. So using this, okay, and also just for the remainder, maybe we can similarly sin hyperbolic as this e to the power x minus e to the power minus x divided by 2. Right, so what we get, so from here we get z will be equals to 4 plus 2 times, this could be written as 2 times cos hyperbolic, so we get 4 times cos hyperbolic. Instead of x we will have 2 beta j. Alright, so I can write z is equals to, so our partition function, that will be equals to 4 times 1 plus cos hyperbolic, or it will be common, 2 beta j. Okay, so we have found the partition function. Now we have to find the average energy. So for average energy, we know that average energy is given by summation of I ei e to the power minus beta ei divided by z, the partition function. So just put the energies. So for energy 0 value, the summation terms, those will be 0. Other terms would be, I will have 2 terms with energy 2j e to the power minus beta 2j, and 2 terms with energy minus 2j e to the power beta 2j. This whole divided by my partition function, which is 4 times 1 plus cos hyperbolic 2 beta j. Alright, and from here I can take 4j common. So what I will take minus 4j common. Okay, so in that case I will have e to the power beta 2 e to the power 2 beta j minus e to the power minus 2 beta j divided by 4 times 1 plus cos hyperbolic 2 beta j. Alright, again as we have seen, the sin hyperbolic is e to the power x minus e to the power minus x divided by 2, and also we can cancel out 4 from up and down, from numerator and denominator. Okay, so numerator we can just cancel, cancel 4. So we will get here 2 times sin hyperbolic 2 beta j divided by 1 plus cos hyperbolic 2 beta j. Okay, so what we are getting, let me see if okay, find it further. So okay, so we can just see the answer here. So our energy, average energy of the system, it comes in minus 2j sin hyperbolic 2 beta j divided by 1 plus cos hyperbolic 2 beta j, and this is our final answer. Okay, so our final answer is minus 2j times. Okay, so our final answer is minus 2 times j sin hyperbolic 2 beta j divided by 1 plus cos hyperbolic 2 beta j. Right. So this is what we have to find. Let's go on to problem number 3. Okay, so in problem number 3, what we have to do is consider a one-dimensional. Okay, so again we have an Ising model. So consider a one-dimensional Ising model with n spins at very low temperatures when almost all spins are aligned parallel to each other. Let's start from problem number 3 again. So what we have is consider we have an Ising model again. So consider a one-dimensional Ising model with n spins at very low temperatures when almost all the spins are aligned parallel to each other. So we are considering at very low temperature they are all in a ferromagnetic order, all the Ising n spins in a one-dimensional chain. So in a one-dimensional case, so we have a 1D Ising model. Okay, so all the spins they are aligned in ferromagnetic order. Okay, so we are doing problem number 3. So in problem number 3, as I was saying, so we have a one-dimensional Ising model with n spins at very low temperatures. Can you please mute yourself? If you want to ask question, then it's fine. Otherwise, can you please mute? Because then. Okay, thank you. Alright. Okay, so we are doing problem number 3. So in this case, we have a one-dimensional Ising model with n spins at very low temperatures when almost all the spins are aligned parallel to each other. So we have a kind of a ferromagnetic kind of configuration. Now there will be a few spin flips with each flip costing an energy 2j. So what we are going to do, we have like n spins in 1D, and there are going to be few spin flips. Some of the spins we are going to flip, and whenever we are flipping them, we are it will cost us an energy 2j. So the ground state is when all the spins are parallel to each other, but if we flip a spin within the system, then that will cost us an energy 2j. Okay, so that we can so in the configuration with r spin flips, the energy, so according to this, the energy of the system we can write it as minus nj plus 2rj. So here you can see that if where r is the number of spin flips, so if r is 0, here we are not doing any spin flip, so the energy formula is just minus nj. So the minimum energy Yeah, good evening. Audio, my voice is not. Is it better now? Can you? It, uh, this time it is. So it's better now or not? Can you hear me now? Am I audible? Yeah, good evening. Am I audible now? Now? Can you hear me now or is it? Hello? Can you hear me now or can you hear me now? Yeah, I've been checking, but then in the recording the voice was okay. Am I audible now? Am I audible? Hello? Yes, that's the message. One minute. Am I audible now or not? I don't know, like in the recording actually there is no issue. You are saying that I am not audible. Can you hear me now? Uh, Shahab? Hello? Oh, okay, so, okay, sorry. Okay, my mistake. I was okay. Can you hear me now? Sorry about it. Am I audible now? Now, yeah, I muted myself earlier. Sorry about that. In the recording it was going, but there was no one in the session. It's audible now. Okay, yeah. Sorry about that. Actually, there was no one in the live session, so I muted it because there was some problem with my laptop. So I muted my laptop, and in the recording there was no issue. So I thought, okay, sorry about that. Okay. So we have already done problem number 1 and 2 that you can see in the recording written on the YouTube. So let's just do the problem number 3. Sorry about that. I muted myself there. Sorry. Okay. So we have this problem number 3. So in problem number 3, what we have to do here, we have to consider a one-dimensional Ising model with n spins at very low temperature. So we have a ferromagnetic kind of case. Okay, we have a 1D case where all the n spins they are configured parallel to each other. Okay, so we have like this ferromagnetic kind of case, a 1D case of n spins. Then and that we have at a very low temperature. Now there will be few spin flips. So few spin flip means like I take one of the spins and I flip that spin down. Okay, and then in that case what it is saying is that for each spin flip case we have to pay an energy 2J. Okay, so basically as we know, like if we have like this Ga basically kind of tells you the bonds within this Ising models. So if I flip one of the spin, I have to give an energy. We can understand that I have to basically give an energy 2J to flip a spin. Okay, so according to this, so we can write our energy functional here as written here. So energy functional we can write as energy we can write as minus Nj plus 2 times Rj. Okay, where R is the number of spin flips and the number of configuration is NCR, where R varies from 0 to n. Okay, the spin flips could be either 0 to n, and accordingly we will have the number of configurations that can have that spin flip, because basically if you have like, sorry, I don't know why. Like if you have taken one spin flip, so and if you have n, so you can actually spin any of this spin, okay, among this n spin you can flip. You will have like nc1 spin configuration. You can either flip this one or this one. So accordingly we will have nc1 equals to n times n types of spin configurations, which will have the same energy as as you will get by flipping one of the spin, okay. And we have to find the partition function for this system, okay. So for this type of question, so first of all, you know the partition function, okay. So we know the partition function is given by summation over I e to the power minus beta ei. So now partition function, so first, so what we will do in this type of question, we will find the partition function for one particle, for a single particle instead of or. So partition function for single particle, it means our capital N is equals to 1, okay. Here you can see the energy conversion is minus nj plus 2rj. So if R is basically 0, we are not flipping any energy, flipping any spin, then the energy will be lowest when all of them, they have the energy is minus nj. It means all the spins, they are aligned parallel. That is our minimum energy. And then if we to flip one, if R equals to 1, then you have to give energy. You have to give an energy plus 2j. Now the partition. So for this thing, for this kind of problem, when we have n spins, what we can do is we can first find the partition function for single particle, taking capital N equals to 1. So in that case, so partition function for one particle. So for this, what we can have we can have the so that we can have either two configuration. Either we will have the spin in one direction, or we will flip it. So R value will go from 0 to 1. So here basically in this energy functional, minus nj, that is a constant, plus 2rj, and R is varying from 0 to capital N. And since our capital N is equals to 1, so our partition function will have R equals to 0 to n e to the power minus beta for energy for one particle only. It means capital N equals to 1, okay. And okay, so in that case our z1 will be equals to that will be equal to R equal from 0 to 1 e to the power minus beta. Now the energy will be for n equals to 1, okay. So for this is the total energy for E of n, you can say. So basically let me just write it as E of n. So energy of the n spins is given by minus ng plus 2r times j, okay, sorry, 2r times j, okay. So here we have to write the energy for one particle only, single particle. We are writing the partition function. So this will become minus j n equals to 1 plus 2rj, and the R value could be, in one case there will be no spin flip, and other case there will be a spin flip, okay. So R value could be 0 and 1. So in that case z1 will become e to the power for R equals to 0, it will be just e to the power beta j, and or for R equals to 1 it will be e to the power beta j minus 2j, okay, sorry, minus 2 beta j. So z1 will be equals to e to the power beta j plus e to the power minus beta j, and again as you might know, cos hyperbolic x. So this we have used several times in our sessions. It is e to the power x plus e to the power minus x divided by 2, and sin hyperbolic x, that is given by e to the power x minus e to the power minus x divided by 2. So using that, this partition z1 will be equals to 2 times cos hyperbolic beta g, okay. So this will be our partition function for one particle, but we have to find the total partition function. So now what we can do is we can write the partition function of n particles, that will be given by z1 whole to the power n, okay. So for this kind of problem, this is how you can solve. So this is the partition function for n particles. Okay, it means our Zn, that will be equals to 2 cos hyperbolic beta j whole to the power n. Okay, but now the problem is not solved here, because we have to consider basically something called multiplicity as well. So for n spins, we have to consider omega, which will be the spin multiplicity, which is given by 2s plus 1 whole to the power n, and here the s will be equals to, so it is given that Ising model with n spins. So since it is not given, we can, I guess it is not given, it is spin half particle or not, but we can consider it to be a spin half particle, so we can consider capital S to be S equals to half here, because general, okay, so it is not written here, but I guess in this problem it is basically a spin half particle. So our multiplicity, so the multiplicity will come as 2 to the power n, and you can consider it in this sense as well. Basically, we have written this for the n particles, we have written this just whatever was for the one particle, we just give it to the power n. But again, each of the spins, they have like two cases. One case could be like all the spins they are in this direction, or I could have started with all the spins in the down direction as well, because there is flipping is possible. So for each of them, this two possibilities are there. So we have to basically take into account all of them for n spins. So we have to take into account this multiplicity for n spins. So we have to divide it by this term here. So the partition function, that the net partition function for this system, that will be equals to whatever is for the n particle divided by the multiplicity. So this is basically the formula that you can use. So in statistics, when we have this kind of problem, we have to consider this multiplicity. So you will have to divide it by this omega, multiplicity omega. So what we will have, we will have 2 cos hyperbolic beta j whole to the power n divided by the multiplicity, which is 2 to the power n. So what we will get, so our partition function z will be equals to, that will be equal to cos hyperbolic beta j to the power n, capital. Okay, so that's the answer. Any doubt in this problem? Okay, then let's move on to problem number 4 then. Okay, so again problem number 4 is also of one of the Ising system only. So what is given to us, the partition function of a system of n Ising spin is z equals to lambda 1 to the power n plus lambda 2 to the power n. So in this case the partition function is already given to us, where lambda 1 and lambda 2, they are some functions of temperatures but are independent of n. Now if lambda 1 is greater than lambda 2, find the free energy per spin in the limit that n tends to infinity. So this is our problem. We have to find the free energy per spin. Okay, and partition function is already given to us, so we have the relation between free energy and partition function that we have to use, and the condition is given to us that we have to consider that lambda 1 is greater than lambda 2, and we have to find it in the limit n tends to infinity. So given is the partition function of n spins, right? So this is equal to that will be equals to lambda 1 to the power n plus lambda 2 to the power n. Now condition is given to us that lambda 1 is greater than lambda 2. Okay, this is the condition that is given to us. So what we can do is, in this partition function z, I can take lambda 1 common, lambda 1 to the power n I can take common, then we are left with lambda 2 1 plus lambda 2 by lambda 1 whole to the power n. Okay, now here we can see that now and also we have to consider n tends to infinity, that limit also we have to consider. Now for large n, which is given to us like n tends to infinity, we can see that here first of all let me just mention that lambda 2 is greater than lambda 1, that means lambda 2 by lambda 1 is less than 1. Okay, so this we already have, lambda 2 by lambda 1 is less than 1. And then for large n, that is n tends to infinity, what we can write is this lambda 2 by lambda 1, which is already less than 1. So you have a value which is less than 1, and if it is to the power n, where n is tending to infinity, then this will tend towards 0. Okay, since lambda 2 by lambda 1 is less than 1. Okay, therefore what we will have our partition function will be approximately equals to just lambda 1 to the power n. Okay, now we have to find the free energy. Now to find the free energy, we know the relation free energy is given by if we have the partition function, it is given by minus kBT ln of this z, which is our partition function. So just f will be equals to minus kBT ln of lambda 1 to the power n. So what we will get is free energy will be equals to minus n kBT ln lambda 1. This is our free energy. Okay, so this is the and what we have to find, the free energy per spin. Okay, sorry, we have to find it to be per spin, and total number of spins are capital N. So the free energy per spin so that will be given by F divided by this N. So it will be equals to minus kBT ln lambda 1. It is log number. Okay, and this is our final answer. Okay, any doubt in this one? Alright, okay, then let's move on to problem number 5 then. So in problem number 5, this is related to superconductivity. So in problem number 5, what is asked is if the critical magnetic fields of a superconductor at temperature 4 Kelvin and 8 Kelvin are 11 milliampere per meter and 5.5 milliampere per meter, then what is the value of the critical temperature? So for this we already know that the critical, so this is the formula for the critical that magnetic field, that is given by H naught 1 minus T by Tc whole square. Okay, where and this Hc is critical magnetic field at temperature T. Okay, so critical magnetic field is a function of temperature. So, and critical magnetic field is basically the magnetic field because of which your superconductor goes from superconductor to normal conductor. If you apply this critical magnetic field, it will go from superconductive to just that normal conductor. Now where Hc is critical magnetic field at temperature T, and H naught is the critical field at 0 Kelvin. Okay, you can put T equals to 0 and Hc will be equals to H naught. Okay, then so we have to find what is the value of, okay, so we are given two temperatures and two critical field values. okay, at two different temperatures. So we have to find the critical temperature, we have to find the TC value. Okay, basically we have to find what is TC. Okay, so let at T equals to T1 equals to 4 Kelvin. Okay, now this critical field, it is given to us 11 milliampere per meter, and at T equals to T2 equals to 8 Kelvin, our critical field, okay, this is given to us 5.5. Okay, so therefore using that this above formula, okay, using this formula we can write Hc T1 will be equals to H naught 1 minus T1 divided by Tc whole square, and Hc T2 equals to H naught times 1 minus T2 divided by Tc whole square. So now we take the ratio of HCT1 and HCT2. So we have HCT1 divided by HC. So I can write it as TC whole square minus T1 whole square divided by TC square minus T2 square. Okay, so from here this is just simple algebra actually. TC square minus T2 square, that will be TC square HCT2 times TC square minus T1 square. Okay, so just take TC square common, so I will have HCT1 minus HCT2, that will be equals, we get HCT1 T2 square minus HCT2 T1 square. So from here you get the formula for critical temperature, that will be equal to HCT1 T2 square minus HCT2 T1 square divided by HCT1 minus HCT2 is to the power 1 by 2. Alright, so now we so we have this formula now for our critical temperature. Okay, HCT1 T2 square minus HCT2 T1 square divided by HCT1 minus HCT2 to the power 1 by 2. Okay, alright, okay, that's correct. Okay, so now we just have to put in the values. Okay, so that will be our HCT1 was 11 and this T2 was 8, so it will be 64. HCT2 was 5.5 and T1 was 4, it will be 16 divided by 11 minus 5.5 is to the power 1 by 2. So if you just calculate it, let's take the values. So basically what you will get is you will get TC will come as 616 divided by 5.5 to the power 1 by 2, which is approximately going to be 10.6 Kelvin. Okay, so this you can check. Okay, so this will be our critical temperature. Okay. Any doubt in this one? Okay. No? This was a basic question. All you have to do is you need to remember this relation. You have to remember that relation, this how to find the critical field, critical magnetic field for the superconductor at any temperature T. That is given by this formula. Alright. So let's move on to the next problem number 6. So in problem number 6, what we have is the thermal conductivity of a given material reduces. So in problem number 6, what we have is the thermal conductivity of a given material reduces when it undergoes a transition from its normal state to the superconductive state. Provide the reason behind the physical phenomenon. Okay, so this is a fact. Okay, so we know that the thermal conductivity of a given material, it reduces when it undergoes a transition from its normal state to the superconductive state. So we have to specify like what's the reason behind this. So this is not a numerical problem, so I will just write it down. Okay, so there is a gap opening on transition to the superconducting state so that a minimum energy is required for the excitation of each electron from a state below the gap to a state above the gap leading to a reduction in thermal conductivity. Okay, so basically what happens is when we do this transition from this normal state to the superconducting state, then what is happening, there is a gap opening on transition to this superconducting state, so that we require a minimum energy for the excitation of each electron from a state below the gap to a state above the gap, and that leads to the reduction in the so basically for thermal conductivity, when you provide for thermal conductivity, we need to excite the electrons. And but what happens is that when we go from transition from a normal state to the superconductive state, then there is a gap opening happens. Because of that gap opening, a minimum energy will be required to excite the energy, to excite these each of the electrons which are below the gap to the above the gap, because of which there is going to be a reduction in our thermal conductivity. Alright, so this was not a numerical problem, it was just like a theoretical problem, you can say. Any doubt in this one? So let's go to our problem number 7. So the next 3 problems, they are from this book. Just 1 minute. 1 minute, I guess. Just 2 minutes, I guess. There is some issue with it. Just one. Sorry about that delay. Yeah, I was just there was some problem with the laptop, but okay. So let us start again. So the next three problems that I have taken from this book. Okay, so earlier also we have done some problem from this book. The book is Introduction to Solid State Physics by Charles Kittle. So chapter 10 of this book it is on superconductivity, so you can check it out for the reference. Okay, and the next three problems they are from this chapter of this book only. Okay, so our first problem is regarding the London penetration depth. So the London equation that you might have seen in your lecture regarding the superconductivity. So in this problem, what you have to do is take the time. In the first part, what we have to do is we have to take the time derivative of the London equation to show that this del G vector by del T, G is our current density, as you know, that is equals to C square upon 4 pi lambda L square times E vector, where E vector is your electric field and lambda L is your penetration depth. And in the b part, what you have to do, like if m dv by dt, you can write it as 2 times of e vector, alright, which is just like your force. As for free carriers of charge q and mass m, we have to show that this lambda L square is given by this equation. Okay, right? Okay. Now for this, first remember that what is given by the London equation. So from London equation, one of the form of the London equation uh, is given by this, minus 1 by mu naught lambda L square times A vector. Okay, and E vector, you know, that is your gauge potential. So this is in SI units, but generally we are going to use the CGS units. And in CGS units, the same formula is given by J vector equals to okay, so I'm using capital J. In the problem, I guess it is small j, but I'm using capital J. It is given by 4 pi lambda L square times A vector. It is CGS units, and we are going to use this one within the CGS units. Now, so here we know that, okay, so this thing you might know from your basic mechanics, that the electric field will be given by minus of the gradient of this phi, which is your flux, times and minus 1 by c del A vector by del T. Okay. Now here in this case, okay, so let's say this is our equation number 1. Now when we differentiate the London equation, okay, London equation is given to us. So when we differentiate the London equation, what we are going to have, okay, so this is our equation, this is the equation, this equation we are going to use. So we'll get del J vector by del T, that equals to minus c upon c divided by 4 pi lambda L square del A vector del T. Okay. Now from this from 1, okay, from 1, this equation that we know from simple mechanics. If you know this gradient of gradient of phi, we are just taking 0, okay, that we can take. So del of A vector by del T, I can write as minus c times of E vector. Okay, so switch my light. Okay. Alright, so let me just repeat once again. So we are doing this problem. This is we have like 3 more problems for this session, and all 3 of them I have taken from this book, Introduction to Statistics by Charles Kittle, chapter 10, that is on superconductivity. In this problem, we have to take the time derivative of the London equation, and then we have to show this thing. And again, we have to use this relation for the free carriers to show what is our this relation where lambda L is our penetration depth for the superconductor. Okay, and J is our current density. So the London equation form that we are using is this one. The J vector is equal to minus c divided by 4 pi lambda L square times A vector in the CGS units. Now we know from simple mechanics we can write the electric field as minus gradient of phi, which is your flux, minus 1 by c del A vector by del T, that is your gauge potential. Okay, your magnetic field B vector is curl of A vector. Okay, so that is that gauge potential, the magnetic field. Then we just have to differentiate this equation, this London equation. So we differentiate it with respect to T, and then from this relation that we know, considering phi to be 0, the flux to be 0, or this gradient of phi to be 0, you get del A vector by del T equals to minus c times of E vector. Therefore, this del J vector by del T, that will come as c square. Okay, so just put del A vector by del T, this thing in this equation, we get c square upon 4 pi lambda L square times E vector. Let's say this is our equation number 2. Now we know that our current density J, we can write it as n times q times V vector for free carriers. So let's say n is the concentration of the free carriers and q is the charge, as given in this problem as well. We have to consider like charge q here. So if we use that, then in that case, therefore this del J vector by del T, that will come as nq times del V vector del T. Okay, and this is given to us. Okay, this is also we can use like m dv vector by dt is equals to q times of E vector. So this dv vector by dt, I can write it as nq times q by m times E vector. So what we get del J vector by del T. Okay, what we have to part A, part B. We have to show. Okay, so sorry. So first of all, we were doing part A, and in part A we have done this part A. So this was our part A, what was done here. This is what we have to do. Del J vector by del T is c square upon 4 pi lambda L square times E vector. Okay, this was our part 2. Now for part B, we are using J vector for the free carriers as given in this part B. Okay, we have to consider free carriers, so we can write J vector nq times V vector, and then if I take the derivative in that case and using this iteration, and d vector dt equals q times of E vector, we get this. So del J vector by del T, that will come as nq square n times E vector. This is here our equation number 3. So from now comparing 2 and 3, so 2 equation is our part A, what we had proved for part A, and this is our equation number 3. Then comparing 2 and 3. Okay, so if you just compare 2 and 3, what you will get? So here you can see that it is del J vector del T and q square m E vector. So it is just this this two, they are different. So what we get c square upon 4 pi lambda L square, that will be equal to nq square by m. So from here our lambda L square will be equals to, that will be equal to mc square upon 4 pi n q square. Okay, and I guess and this is what 4 pi n q square, and this is what we have to prove. Okay, lambda is mc square 4 pi n q square. Okay, this is what we have to prove. Okay, this was the part A, and this is our part B. Okay, any doubt in this one? So here we just have to do the differentiation of the London equation, and then we just have to use this equation for the electric field. Okay. So let's go to our next problem, problem number 8. So in problem number 8, this is also from the same Charles Peters book, problem number 1 of chapter 10. So in this problem, what is written to us? We have a magnetic field penetration in a. So this is regarding the magnetic field penetration in a plate. So the penetration equation, we can write the penetration equation as this: lambda square del square B equals to B, which is also one of the form of your London equation. Now we have to show that that B as a function of x inside a superconducting plate perpendicular to the x-axis and of thickness delta is given by Bx is equals to this Ba times cos hyperbolic x by lambda divided by cos hyperbolic del by 2 lambda, where Ba is the field outside the plate and parallel to it, and here x equals to 0 is at the center of the plate. And then from that B of x, when we have found, we have to find the effective magnetization, and it is given that the effective magnetization is given by, in the plate, is given by Px minus Ba equals to 4 pi times mx, and then show that in CGS this 4 pi times mx is equals to this in the limit that this delta is much less than lambda. This limit we have to use, and then in SI unit you can just isolate and you can just replace 4 pi by mu naught. Let's just change in the units. Okay, so first of all, what we are given to us. Okay, we know. So this is also one of the form of London equation. So from London equation we know that. So we are just talking about in the so the equation is this basically. London equation is this, but we are talking in 1D case only. So this equation I can write it as d square b by d square b dx square equals to, that will be equal to 1 by lambda square b. Let's say this is our equation number 1. So what is given in this problem? Basically, it's the same thing that you have seen. Similar thing you have seen in the lecture as well. But here basically, what was given is that at x equals to 0, after x is 0, there was superconductivity we have considered, and then we have applied some magnetic field outside. So what is given in this case is that for this x-axis, basically from minus delta, you have a superconducting plate of thickness delta, and the center and at x equals to 0 is the center of your plate. Okay, it is given that the x equals to 0, that is at the center of the plate, and the plate thickness is delta. Okay, so basically at x equals to 0, it is your center, and your plate is from minus delta by 2 to delta by 2. So this complete region, this is your superconductor. Okay, from x equals to minus delta by 2 to delta by 2. So outside this, and it is given that outside this you have a magnetic field BA, and this direction, and here also, sorry, okay, so y-axis you can consider like this is your magnetic field. So at so here you can see that basically your magnetic field is equals to that is BA outside your superconducting plate, and we have to show that the inside it is given by this, and we know that inside the magnetic field follows this London equation, which is given here, this equation number 1. Now to and also so basically what we have this equation number 1, and then we have the boundary conditions that b at plus minus del by 2, that should be equals to BA. Okay, because that is the outside this superconducting plate. So now solving this would be completed. So one way to prove that this bx actually follows this equation is just that basically that whatever the bx that is given to us, it should satisfy this equation, this London equation, as well as it should satisfy the boundary condition as well. So for the part A, where we have to show that bx provides supposes, so we will just let's assume that our bx will satisfy both of this equation number 1 and 2. Okay, this London equation number 1 and this boundary condition, that is what is given to us, BA cos hyperbolic x by lambda, and it is equal to cos hyperbolic del by 2 lambda. So we will assume that it satisfies let's say it satisfies 1 and 2. Equation number 1, equation number 2, which is a London equation and boundary conditions. Now we need to check if our assumption is correct. Okay, so basically we need to check if this bx that is given to us, is this the solution of this equation or not, that bx inside superconductor is given by this equation, it could be given by this equation or not. So for this, first we have to check if this bx satisfies both equation number 1 or 2 not. So first what we will do, we will check if BA of x satisfies 1, equation 1, which is our London equation. So here again a reminder, okay, again so here we will use this two formula. So basically as you know, basically we have to put b, and we have to take the derivative of this b. So for that we need to remember that this d by dx of cos hyperbolic x that is equals to sine hyperbolic x. Okay, so if you take the derivative of cos hyperbolic x, it will be sine hyperbolic x, and we can prove it as well quickly, which is it's not that difficult. So proof also we can give. So it is d by dx of cos hyperbolic x, d by dx of e to the power x plus e to the power minus x divided by 2. So e to the power x differentiation will be e to the power x, e to the power minus x differentiation minus e to the power minus x. 2 is just a constant, and this we know this is basically the formula for sine hyperbolic x. Okay, so that's why d by dx of cos hyperbolic x is sine hyperbolic x. And the second formula, similarly, this d by dx of sine hyperbolic x, so that comes as cos hyperbolic x. Okay, so proof of all this, d by dx of sine hyperbolic x, that will be d by dx of e to the power x minus e to the power minus x divided by 2. So e to the power x differentiation will be just e to the power x, e to the minus x will give you a minus sign, so minus sign plus 2 is a constant, and this we know that is equals to cos hyperbolic x. Alright, so this we need to know, we need to remember. Now so let's just continue with our problem. Okay, so this is our equation now. So first we need to check that whatever our b of x is, it satisfies this. So let me just write again. B of x is given to us as ba times cos hyperbolic x by lambda divided by cos hyperbolic delta by 2 lambda, and the London equation that it has to satisfy d square b dx square, or in this side del square b del x square equals to, that will equals to 1 by lambda square b square. Okay, so this is the equation that we have to satisfy. So if we take the left hand side, okay, so we have to find this del square b del x square, b of x basically, del square b of x by del x square. So that will be del square del x square. I can take this, that is ba times cos hyperbolic x by lambda divided by cos hyperbolic delta by 2 lambda. Okay, so just take the constants out. This cos hyperbolic delta by 2 lambda, we have del square by del x square, or I can write d by dx square here, d square by dx square, cos hyperbolic x by lambda. So that will be ba cos hyperbolic delta by 2 lambda, we can write it as d by dx of cos hyperbolic x by lambda. Okay, so now as we have already know, the differentiation of cos hyperbolic x will be sine hyperbolic. We have a constant and the 1 by, and then we have to take the differentiation of x by lambda, which will give us 1 by lambda. So 1 by lambda will be constant. We get d by dx of sine hyperbolic x by lambda, and then you again take the differentiation, you get cos hyperbolic delta by 2 lambda 1 by lambda square cos hyperbolic x by lambda, and basically this 1 by lambda square times what we are getting ba times cos hyperbolic x by lambda divided by cos hyperbolic delta by 2 lambda, and that is basically your b of x. So what I am getting, we are getting 1 by lambda square times b of x, which is equals to our RHS value. Okay, that is equals to our RHS. So this is our London equation, and we are getting the same thing on the right hand side. Okay, so hence proof, we can say that basically this is hence proof. Okay, so our b of x satisfies equation 1. Okay, so it satisfies equation 1. Now we have to just check if which is the run-down equation. Okay, now we also have to check that if b of x satisfies the boundary conditions or not. Satisfies equation number 2. So we have to check that b, here we can see that b of x at plus minus delta by 2. So we have to find b of x. So the boundary condition is the boundary condition that we have is b at x equals to plus minus delta by 2. It should be equals to ba. Okay, and here b of x, we have it is ba cos hyperbolic x by lambda divided by cos hyperbolic delta by 2 lambda. So first we will first we will find b at x equals to delta by 2. So that will be equals to just ba times cos hyperbolic delta by 2 lambda divided by cos hyperbolic delta by 2 lambda. So that will be equals to ba, because this and this will cancel out. Okay, so here what we are getting, we are getting b at x plus 2 del by 2, that is coming as ba. Now therefore we can find that b at x equals to minus delta by 2. So that will be equals to ba times cos hyperbolic minus delta by 2 lambda upon cos hyperbolic delta by 2 lambda. Now cos hyperbolic minus x is basically cos hyperbolic x. So what we will get is we will get ba times cos hyperbolic delta by 2 lambda divided by cos hyperbolic delta by 2 lambda. Then it's out. So what we get is b. So we get so here also we get b at x equals to minus del by 2 is equals to, that will be equals to ba. So so it satisfies our bond. So b of x satisfies satisfies equation number 2, which is our boundary condition. Right. So therefore b of x is our answer. B of x satisfies this equation. This satisfy b of x is the magnetic field inside the superconductor for this problem, because it satisfies the random equation and it also satisfies the boundary condition as well. Okay. So let me just see. And so this was our part A. Now in part B we have to find the magnetization mx. Now 4 pi of mx is given to us. It is given by b of x minus ba. So I can write ba cos hyperbolic x by lambda divided by cos hyperbolic delta by 2 lambda minus b of a. So what we get? We get 4 pi times mx. So that is going to be equal, that will be equals to ba times cos hyperbolic x by lambda divided by cos hyperbolic delta by 2 lambda minus 1. And in this b part, the condition is given to us. We have to take condition that delta is much less than lambda. Now for basically for delta much less than lambda, this condition that we can write this cos hyperbolic x by lambda. Now this x is between, basically for superconducting plate, x is between minus delta by 2 to delta by 2, and if delta is much smaller than lambda, then this x value set is also going to be small, and we can approximate it as 1 plus half of x by lambda whole square. And similarly for cos hyperbolic, delta by 2 lambda. Okay, so this is the so we can approximate it as this is from the expansion of this cos hyperbolic function. I can write it as half of del by 2 lambda whole square. Okay, so using this we can write basically, therefore we can write our 4 pi times m of x, we have written here, so I can approximate it as b of a, okay, 4 pi times m of x. Okay, we can approximate it as b of a times we can write 1 plus half x divided by lambda whole square plus 1 plus half delta by 2 lambda whole square minus 1. Okay, so we can approximate our multiplication like this, and I can take this out, this constant, which is 1 by 2 delta by 2 lambda whole square, so that will be equals to 1 plus half x by lambda whole square minus, we will have 1 minus half del by 2 lambda whole square. So we can approximate it. So what we can write it as dA upon b divided by half del by 2 lambda whole square times when we consider, what we will get is half of x by lambda whole square minus 1 by 8 of del by lambda whole square. Now here since we know that delta is much less than lambda, now since delta is much less than lambda, we can say that delta by lambda is much less than 1. Okay, so delta by lambda is much less than 1, therefore delta by lambda whole square is also much less than 1. This square will be way more less, so therefore this implies our 4 pi times m x, we can further approximate to, it will be b a times, I can take, now here from here I can take 8 times of lambda square common, and so we are left with and I will take a minus sign also common, minus 1 by lambda square, I will take a minus common here. So what we will get del square minus 4x square. It will be del square minus 4x square. Yes, and this is our answer. So I can basically write 4 pi m x like this. Okay, and this is what we have to prove. We have to prove that 4 pi m x equals to minus ba times 1 by 8 lambda square, and 1 divided by 8 by lambda square, lambda square, del square minus 4x square. That is what we have derived here. Okay. Any doubt in this problem? Okay, so let's move on to our next problem. Just one minute. Okay. Okay. So this is the last problem of this session. So in this, this is also problem number 3 from the chapter 10 of Introduction to Solid State Physics by Charles. So this is the problem where we have seen that in the lecture also it was said that basically in the model we consider that in the superconducting state basically electrons we can consider the electron density of two types. One will be the electron density of the normal electrons, and the one will be the electron density of the superconducting electrons. So in that, so this question is also based on that model only. So let's consider like two fluid model of the superconductor. So on the two fluid model of a superconductor, we assume that at temperatures are okay when our temperature is less than our critical temperature, so we are in our superconducting state. The current density may be written as the sum of the contributions of normal and superconducting electrons. So we can write our G vector as Gn plus Gs, where Gn that is for the normal electrons. So we can write it as sigma naught times of E vector, and Gs is given by our London equation as we have seen. Now here sigma naught is the ordinary normal conductivity, which is decreased by the reduction in the number of electrons at temperature T as compared to the normal T. Okay, so it is decreased by the reduction in, so this sigma naught, it is ordinary, so sigma naught is this ordinary conductivity which is decreased by the reduction in number of normal electrons. So since the number of normal electrons will decrease in the superconductor because of the increase in the electrons in the superconducting state, so this sigma naught will also decrease at temperature T as compared to normal state. Now neglect initial effects on both Gn and Gs, and we have to neglect any initial effect on G and Gs. So in the first part, what we have to show show the Maxwell equations that the dispersion relation connecting wave vector k vector and the frequency omega for electromagnetic waves in the superconductor is given by this in the CGS and the SI unit. We will focus on the CGS units, and then you can convert it to the SI units. Okay, where lambda L square is again our depth penetration for superconductor, and with n replaced by ns. Okay, in this case for lambda L we have to replace n by ns. Okay, we will replace n by ns, and recall that this curl of b vector that is equal to minus del square b. Okay, remember that for this lambda L square, this n is replaced by the ns, which is number of electrons in the superconducting state, superconducting electrons. Alright, and then we will see the part B. So first of all, this lambda L, that will be given by mc square upon divided by 4 pi, and instead of n, write n, it is given by nq square, and instead of n we have to write the ns, and q instead of q is write e. Okay, so because we have electrons, so it is the mc square upon 4 pi ns times e square. This is in the CGS units, it is we are going to use, and in case of the SI unit, it is given by epsilon naught mc square upon divided by n e square all to the power 1 by 2. This is an SI unit. Okay, but we will do the CGS unit, and then you can try to convert it into the SI unit. Now in as you know, in CGS units, in non-magnetic material, B and H are identical. Okay, so otherwise there will be a factor of mu between B when we convert from B vector to H vector. So I am writing this because basically these equations, instead of B vector we actually write the H vector. The curl of H vector is given by this 4 pi times J vector by C plus 1 by C del E vector by del T. But since in the CGS units H and B are same, so I will just replace this H by B. Okay. Now here we know this J vector that will be equals to Gn vector plus Js vector, and here this Gn vector that will be equals to sigma naught times E vector from the Ohm's law. Gn vector is equal to sigma naught times this, and Js vector that is given by our London equation, it is given as minus C upon 4 pi lambda square times the A vector, which is our gauge potential, and curl of A vector is equals to B vector. Okay, and here remember and this right on the side here curl of A vector is equals to B vector. We will use it later as well. Okay, so now this J vector basically that will be given by then Jn vector plus Js vector. Okay, that will be equals to sigma naught times E vector minus C upon 4 pi lambda square times A vector, where lambda is your this lambda L only. Okay, I'm just writing it as lambda L. Okay, so we have the J vector. So now now the curl of B vector. So basically the curl of B vector. Okay, that we have written here. Okay, so that will be given by this. So this implies this curl of B vector will be given by 4 pi C times sigma naught E vector minus C upon 4 pi lambda square A vector plus 1 by C del E vector by del T. Alright, so this is what we have, and then what we have to use, and then what is given, like it is given to us like curl of B. This we have to use. Basically the curl of B is given here. Yes, yeah. Curl of B is equals to, that will be equals to minus del square B. So this is what we will use. So this we already have. Okay, and now we will use this curl of B vector, that is basically equals to minus B del square B. So using this, what we have to take the curl of B vector, which is given by this, which is 4 pi C sigma naught times E vector minus C 4 pi lambda square times A vector plus 1 by C del E vector del T, that should be equals to minus del square B. So from here what we get 4 pi C sigma naught, that will be common, curl of E vector minus 1 by lambda square curl of A vector plus 1 by C del by del T of curl of E vector, that will be equals to minus del square B. Okay, so let's say this is our equation number 1. Now we know the Maxwell relation, because we are in the problem as well, we have to use Maxwell relation. So from Maxwell relation, we know that curl of E vector, it is given by minus 1 by C del B vector by del T. Okay, and also you know that curl of A vector, that is basically B vector. Okay, so we have curl of A vectors and curl of E vector, so we have to replace them and get everything in terms of B, or magnetic field. It is magnetic field intensity, but in the CGS units for the non-magnetic system, magnetic field and magnetic field intensity is same, so that's why we can just take B vector, H vector as B vector, H vector equals to B vector. So use 2 and 3 and 1. Okay, where 1 is basically the equation that we have derived here, and 2 and 3 is Maxwell relation and this definition, curl of A vector equals to B vector. So what we will get 4 pi C times sigma naught minus 1 by C del B vector by del T minus C upon 4 pi lambda square times E vector. So let me just put it as B instead of E vector, and just put this one as B only. And then minus 1 by c square del square b del t square, that will be equals to minus a n square b. Okay. Okay. So or maybe just keep it as b vector for now. Now now from here so if if I take this inside, what we get, I will get minus sigma naught minus 4 pi sigma naught by c square del b vector del t plus 1 by lambda square minus 1 by lambda square b vector minus 1 by c square del square b vector by del t square, it is equals to minus del square b vector. So basically if I just bring it here, what we get is del square b vector minus 1 by lambda square b vector minus 4 pi sigma naught c square del b vector del t and minus 1 by c square del square b vector by del t square. That equals to 0. So that is equation number 4 now. Okay. So now for this, what we have to find the discriminant. So we can assume our b vector. So we have to find b vector which satisfies this equation. So one of the assumptions that we can take is like if b vector is equal to let me just write it a constant something. Okay, let's say this is some constant e to the power iota or okay, that is the z, and z is a constant which is not the partition function. Don't be confused, this is a constant e to the power iota k vector dot r vector minus omega t. Okay, let's say this is our magnetic field. So now we have to find different values. So first we have to find this. Okay, so we have to find these three terms basically, because here to solve this problem we need to find this, and this one. Or maybe let me just put them in different colors. I have to find this, and then I have to find this as well. Okay, so let's just find okay, so let's just find this one first. First we find del square b, so that will be equals to, so if we have to do del square, so what we will have a constant z of z e to the power minus iota omega t, and then this del square will give us del square by del x square e to the power iota k vector dot r vector plus del square. So okay, so basically what we will, let me just write it in once only. What we will, we have del square by del x square plus del square by del y square plus del square del z square. That will be your this del square times e to the power iota k vector dot r vector will become kx plus ky plus kz z. Okay, so we do k vector dot r vector, it will come as this. So if you do this differentiation, basically what we will get, z e to the power minus iota omega t. Now the y and z, they will be constant, so we get e to the power iota ky y e to the power iota kz z, and del square del x square of e to the power iota kx times x plus, similarly we have e to the power iota kxx plus kyy. Let me just write it this kzz times del square d square by dy square dx square dy square of e to the power iota kyy plus we will e to the power iota kyy plus k. So one will be to be kzz, let's take kzz and then the kyy, and then we will have k xx plus kyy, that will be d square dz square e to the power iota kz of kz times c. Right. So from here what we get z e to the minus iota omega t. If you double differentiate what you will get, you will just get e to the power iota, I will get kxx plus kyy plus kzz times iota kx whole square plus to iota kxx plus kyy plus kzz. Okay, because e to the power iota ky will give you iota ky times e to the power iota ky, and then again you take the differential, so you get iota ky whole square times e to the power iota ky, and that I can take there iota ky whole square plus e to the power iota kxx plus kyy plus kzz iota kz whole square e to the power iota kzz. Alright, then we can take some common here. So what we can take, we will get z e to the power minus iota omega t, and this term which is common here, that is basically e to the power iota k vector dot r vector here. Okay, so I can take it out, and I can take out iota square as well, so that will be minus. So what we get minus e to the power iota k vector dot r vector. This I can take common, and we are left with kx square plus ky square plus kz square. Okay, and this is basically this will be basically equals to k square. So what we are doing, we are getting minus of k square. So okay, so we get minus of k square, and then we get z e to the power iota k vector dot r vector minus omega t. Okay, and this is going to be equals to our b vector. Okay, whatever the b vector that we have taken, right? This is our b vector. So what we are getting, minus k square times b vector. So what we are getting here so basically, therefore we can write that del square b vector will be equals to minus k square times b vector. Let's say this is our equation number A. Okay, so this we can replace here. Then this is again red. So we need del b vector by del t as well. So now del b vector by del t of whatever the constant is, it is by iota k vector dot r vector minus omega t. Okay, we get this constant z e to the power iota k vector dot r vector, they come out. We get dy dt of e to the power minus iota omega t. So we get z iota k vector dot r vector minus iota e to the power minus iota omega t. Okay, so what we will get is minus iota times z e to the power iota k vector dot r vector minus omega t, which is again our this is again your b vector. So what we are getting is minus iota times b vector. Okay, so sorry, something minus iota omega actually. Yes. on differentiation with respect to t, we get minus iota omega. So what we get is minus iota omega. So therefore what we get is, we get del b vector by del t, that will be equals to minus iota omega b vector. Let's say this is our equation b. Then similarly we can find this del square b by del t square also now. So this del square b by del t square, so that will be equal to just we already have del by del t value, we already have del b vector by del t, so that is equals to del by del t of minus iota omega b vector. Take the constant out, we have del b vector del t, we already have found it, so that will be equals to minus iota omega and minus iota omega b vector. So what we get, iota square will be equals to minus omega square b vector. So therefore what we have is del square b vector by del t square, that will be equals to minus omega square times b vector. Okay, so this will be our equation number C. Okay, so we have found all the terms that we needed. So now we just have to put this a, b and c value in that equation. So use a, b and c in 4. And c in equation 4. Okay, so a, b, c we have found. Equation number 4 was this, that we have after putting b this before. Okay, this was our equation number 4, and we have found all these 3 marked terms, blue, red and green. We just put in the values. So what we will get, so let me just write this equation again. Okay, so this is the equation, equation number 4, del square b vector minus 1 by lambda square b vector minus 4 pi sigma naught by c square del b vector del t minus 1 by c square del square b vector by del t square, that equals to 0. Okay, that we have, and then we have found all these 3 terms that we need by red, blue, red and green. Okay, using AB, now using this ABC in this equation number 4, what we will get, okay, just put in the values. So instead of this del square b vector, we have del square vector minus k square times b, so I will get minus k square times b vector minus 1 by lambda square, we have b vector minus 4 pi sigma naught by c square, that is minus del b vector into minus iota omega b vector minus iota omega b vector minus 1 by c square, del square b vector is minus omega square b vector, that will be equal to 0. So now b vector, so I can take minus b vector common from all of them, so I will be left with k square plus 1 by lambda square. I will have this 1 minus, we have 4 pi sigma naught omega iota by c square, then we will have 1 minus omega square c square, that will be equals to 0. Okay, so let me see what is the term we need, and we can write okay, so basically just take all the other terms there. So we get k square equals to 4 pi sigma naught omega by c square iota minus 1 by lambda square plus omega square c square, and we can bring c square here, so we have c square k square equals k square c square. What is this one? K square c square, that is equals to 4 pi sigma naught omega iota minus c square by lambda square plus omega square. So this is what we have to prove. So this is our dispersion relation, and you can check that this is the dispersion relation that we have to prove. 4 pi t square c square is 4 pi sigma naught omega I minus c square by lambda square plus omega square. Okay, so this we have found. Okay, this is the dispersion relation. This was our part A. Then in part B, okay, so what we have to do in part B, let me just check. So in part B, what we have to do is, if tau is the relaxation, so now in part B, we have if tau is the relaxation time of the normal electrons and n is the and capital N is their concentration. Show by use of the expression. We have to use this expression. We know. Okay, we know sigma naught is n e square tau by m, and at frequencies omega which are much less than 1 by tau. The dispersion relation does not involve the normal electrons. So basically, in the low frequency range, we have to show that this dispersion relation that we have found for this superconductor below the critical temperature, so it does not involve the normal electrons in an important way, so that the motion of the electron is described by the London equation alone. And the superconductor, as you have seen in the lecture as well, basically the superconductor in this two fluid model as well, basically the superconductor, the supercurrent from this electron which are superconducting one, they short circuits the normal electrons. Okay, so the contribution of normal electrons to this dispersion relation or conductivity is not much. We can actually ignore them. So basically the motion of the electron we can just describe by the London equation only. The London equation itself only holds true if h plus omega is small in comparison with the energy gap that opens up. Now note the frequencies of interest are such that remember that omega is much less than omega p, where omega p is our plasma frequency. Okay, so here, so now for B part, what we have to use is, we have to use this relation sigma naught for the normal electrons. It is nn e square tau by m. Okay, then the equation that we have, okay, that is what is written above, k square c square, that will be equals to 4 pi sigma naught omega iota minus c square lambda square plus omega square. And remember that what is lambda? This lambda square also has the so this lambda square that has only the contribution from the ns, because remember that this lambda is basically equals to as I have written here. So it has contribution from the superconducting electrons only from the London equation. It is equals to this mc square upon 4 pi ns e square to the power 1 by 2. It is mc square upon 4 pi 4 pi ns e square to the power 1 by 2. So the contribution that is coming is nn. It is coming only from sigma naught only. So if this term is negligible compared to this term, then we can say that there is no contribution of this nn electrons. Okay, and we can define this motion of the electrons by this London equation only. So now first of all here, this what you can see that you can check is this 1 by lambda square, that comes as equals to, that you can check, it comes as omega p square by c square. It is, and okay, so this is the you can check the definition of plasma frequency. So 1 by lambda square will be equals to omega p square by c square, the plasma frequency, which will be as given that omega p is much greater than omega c, so it will be much greater than omega square by c square. Okay, so first thing is this 1 by lambda square is much greater than omega square by c square. Okay, so our 1 by lambda square term, so this if I divide by c square here, so this term is going to be much greater than this term. Okay, so this we can see here by this relation that omega p is, since omega p is much greater than omega c, much greater than omega. Okay, so this we can see, and then okay, and as I have written, this lambda is basically equals to mc square upon 4 pi ns times e square. So this I can write it as ns e square by m. I can write as c square upon 4 pi lambda Okay, so this is also that we are going to use. So now what we have to see is, okay, now we are going to see use the second derivation, which is this omega is much less than 1 by tau. Okay, this is also given to us, like omega is much less than this 1 by tau, which is the relaxation for the normal electrons. Okay, so from this what will be 1 by tau? Now from here we have sigma naught here, so from here this 1 by tau will be equal, that will be equal to n e square upon m sigma naught. Okay, so using that I can write this omega is much less than n e square upon m sigma naught. Okay, now I can replace this now since total n is basically n plus ns. Okay, so I can replace okay, so total nn is going to be ns. Okay, you can either replace it by capital N or so basically if omega is less than this, then omega is going to be, if I put this and generally we know that is nn are going to be less than, okay, we know that this nn is less than n of s superconducting electrons are going to be more than this one, so we can write it as ns times e square divided by m sigma naught as well. And here we can see that this we have here ns e square by m is equal to c square upon 4 pi lambda square, so we will use this, and e square m here, this thing, and e square m we have here. So I will just put it I put it here, so what we get, omega is much less than that is basically equals to c square upon 4 pi lambda square. We have c square upon 4 pi lambda square times sigma naught. Okay, then I can take this 4 pi sigma naught here, so 4 pi sigma naught omega, it is going to be much less than c square by lambda square. Okay, so this is also we have found, we have 4 pi sigma naught times omega is going to be much less than this divided by c square, this divided by c square will be much less than lambda naught 1 by lambda square. Okay, and this we can see here, so from this equation, this was our main equation. So we have already proved that 1 by lambda square is much greater than this omega square by c square. So if you just divided this whole by c square, I can write this equation like this. So first I have already proved this 1 by lambda square is much greater than this omega square by c square, and this 1 by lambda square is also much greater than 4 pi sigma naught omega c square, which is here the first term. So we can because of this we can basically write that therefore, okay, so using the both the condition that was given to us, therefore for omega much less than omega p and omega much less than 1 by tau, we can write k square, we can approximately just write it as 1 by lambda square. Okay, and we know that lambda square is basically as we have seen, lambda square mc square 4 pi ns e square. So it will be I can write 4 pi ns e square by mc square. So basically our k square is directly proportional to ns. So it doesn't depend on our normal concentration of our normal electrons. It is basically proportional to the our dispersion proportional to the concentration of our superconducting electrons. Okay, lambda is 4 pi ns. Okay, a whole square actually. Or it was 1 by 2 actually. Sorry, is it 1 by 2 or it was lambda square we used? Alright, okay. Okay, yeah, so here we say that thus the normal electrons play no role in the dispersion relation in the low frequency okay in the low frequency range. right? So this we have proved here. Because our k square dispersion, that will just depend on our concentration of the superconducting electrons. Any doubt in this problem? Okay, so this was the last problem of this session. So so if there are no doubts, then we can just end this session. Okay.